We have a solemn occasion here today. This is our last set of new notes. Welcome to Math in the House. This is Calculus Chapter 9, the final section. Section 4, exponential growth and decay. Okay, so this section we're going to be looking at population growth, hopefully not population decay, and then radioactive decay, or chemicals that lose mass. And population growth, we're going to be talking about populations of people and of all sorts of bacteria and fungi and slime like that. And so then we have radioactive decay and temperature change. Those are going to be the three basic types of problems we're going to work with. So let's get going here. So I'm going to review the things that we start, the first section when we did population growth, proportional population. Let's just go over that one more time. So if we know that population is directly proportional it actually is population growth. Population growth is directly proportional to population. Now you could say that the other way too, but population growth is directly proportional to population. So that gives us the equation dp dt equals kp. So population growth dp dt equals some constant times population. That's direct proportionality. So let's go to town here. We're going to solve this. So we go integral of dp over p equals integral of k dt, which means natural log absolute value of p equals kt plus c. Now, we're going to get rid of the absolute value right away because population has to be positive. So we've got natural log of p equals kt plus c. So now we can go p equals e to the kt plus c. And then we're going to go p equals e to the kt times e to the c. And then we're going to let a equal e to the c. Okay, so that means we've got p equals, let's do this. P equals a e to the kt. All right, so now what we do is we say p sub o equals p at time 0. So what I can do then is rewrite this and say that p sub o equals a e to the k times 0. All right, that means e to the k times 0 is 1, so that means p sub o equals a. So that means I can rewrite this again and say that p equals p sub o e to the kt. All right, so that's what I want you to see then. Anytime you see that population is directly proportional to population growth, then you can automatically say that P equals P sub O e to the KT. So there is a relationship that we don't need to derive every single time. As soon as you realize that dp dt equals Kp, then P equals P sub O e to the KT. Okay, now, let's look at a few other things here. K is called the proportionality constant. Yeah, let's, okay, so K is the proportionality constant. And notice we said population growth proportional to population, so K is the proportionality constant. That's what that means. P sub O is the initial population. Then P is the population at any time t. dp dt is the growth rate. Population growth rate. Now, notice if dp dt equals Kp, now what I can do then is divide both sides by P. So K equals 1 over P dp dt. So notice 1 over P dp dt is the relative growth rate. Notice relative growth rate. If dp dt is the growth rate, then dp dt divided by P is the relative growth rate. That's going to be relative to the population. So if I take the growth rate divided by population, then I get the relative growth rate. Okay, so this is the basic background behind everything that we're going to be doing in this section. So let's check out example 1 in the book. So that's page 613. Now we're not going to do everything that they've done here, but I just want to show you the basic mechanics of what we're doing. So what we see here is in 1990, or 1900 I mean, we're at t equals 0. Okay, then we know the population at t equals 0 is 1650. Okay, so that basically is P sub O. All right, so we know that the population growth is proportional to population, so we automatically have P equals P sub O e to the KT, or P equals 1650 e to the KT. Now, K isn't doing us much good if we don't know what it is. So we need a second point to figure out what k is. So the initial point gave us the 1650, but now we're going to find out what k is by plugging in a second point. So what we're given is that in 1910, the population is 1750. Okay, so that means I could rewrite this then, P of 10 years from the beginning equals 1750. Or the population when t equals 10 is 1750. Okay, so let's plug that in here. So we've got 1750 equals 1650 e to the k t, which is now 10. Now we just solve for k. So we divide both sides by 1650. Now you can just do that right in your calculator. Okay, you take the calculator, go 1750, enter, 1650, divide. Now that gives you e to the k times 10, so then we just take the natural log of that, and then divide by 10. So k is going to equal 1750 over 1650 natural log. So we divide that with e to the k times 10 equals that, natural log of that, and then divide the whole thing by 10. So k will be approximately 0.005884. Okay, now, I gotta check that out. After having a screw up on the last video, I have to make sure I know what I'm doing here. So, 1750 divided by 1650, take the natural log of that, and then divide by 10. 0.005884. Yeah, that's it. Okay. Good thing we have that right. Okay, now, we now have the equation then that P equals 1650 e to the kt. Well, k is 0.005884. T. Okay, so this is the goal, is to get P equals P sub O e to the kt when we have P sub O defined and we have k defined. Now, any other questions they ask us, it's going to be easy. So, first question is, what's the relative growth rate? Well, that's k. Relative growth rate, k. The relative growth rate is 0.005884. What is the population in 50 years? Well, you plug 50 in for t and crank it on out. When will the population be 10,000? You put 10,000 here for p and then solve for t by dividing out the 1650, taking the natural log, dividing out the 0.005884, and you got your t. So, once I get to this point, then I can tell you population for any time you want, and I can give you the time for any population you want. So, this is basically the goal, is we take our P equals P sub O e to the KT. Find P sub O, find K, and then you can answer any questions you want. Okay, so let's cruise onward to the next example. Oh, and incidentally, the relative growth rate, let's just put this up here, relative growth rate is going to be approximately 0.6%. That's so if we want to round that off, we could use percentage, or 0.5884% to be more accurate. All right, on to radioactive decay. So we have radium-226. The half-life of radium-226 is 1590 years. Okay, what that means is in 1,590 years, 100 grams of this radium-226 will have deteriorated down to 50 grams. So in 1590 years, that's how long it takes for any sample of this to decay to half of what it was. Okay, so we're going to start with a sample of 100 milligrams. And so we want the formula. So basically, what this is saying is M sub O is 100. So we've got our general equation, M equals M sub O e to the KT. So now we can immediately put M sub O in, and we've got 100 e to the KT. Now, I need to use the half-life to find the K. So now, what I'm going to do is I'm going to say if the half-life is 1590 years, that's always going to equal M over M sub O. Okay, oh, I'm sorry. That's not going to equal M over M sub O. As I was writing that, I knew that sounded bad. Okay, that's when M over M sub O equals 1/2. Notice M sub O is the initial mass, and M is the mass at any time. So remember, the mass is deteriorating. So M sub O is going to be the most mass we ever have. Well, when the mass we have divided by the original is 1/2, then that's the half-life. So M over M sub O is going to equal 1/2 when T is 1590. So what we do is we say M over M sub O equals E to the KT. Okay, so M over M sub O is 1/2 equals E to the KT. Now what time is that going to be occurring? That's going to be at 1590. Okay, so now all we do is solve for K. How do we do that? Take the natural log of both sides. So natural log of 1/2 is going to equal 1590 times K. Okay, So now all we do is, well, let's make this natural log of 1/2 negative natural log of 2. So that means k is going to equal negative natural log 2 over 1590. Okay, so what I have then is m equals 100 e to the negative natural log 2 over 1590 t. Now, we could work with that, but it's not very convenient. So let's make it more convenient. So what I'm going to do is say this equals 100 e to the natural log 2 times negative t over 1590. Notice what I did from here to here is just I took t over 1590 and the negative and put it in one group and then multiplied by natural log 2. So I haven't done anything except just pull out that natural log 2. Now, next thing I'm going to say is this is 100 e to the natural log 2 all to the power of negative t over 1500, or 1590. So notice a power to a power is multiplying the powers. Okay, what's e to the natural log 2? Right, 2. So I have 100 times 2 to the negative t over 1590. So that is the final version that I can work with. And just like before, now I can give you the mass at any time, and I can give you the time for any mass. So the next question they ask is, what do they ask? I forget. Let's see. Okay, find the mass after 1,000 years. All right, find the mass after 1,000 years. So the mass after 1,000 years is going to equal 100 times 2 to the negative 1,000 over 1,500, 1,590 I mean. So let's just crank that out. So the mass after 1,000 years is going to be 1,000 over 1590, change signs, divide, and I go 2 to that power. So 2 to the negative 0.62, and then multiply by 100, and I end up with 64.6655474644 milligrams. So the mass after 1,000 years is going to be 64.67 milligrams. What else do they want to know? Okay, they want to know when will the mass be reduced to 30 milligrams? Okay, so I want to know what m is going to be. Oops, no, that's not what I want to know. I want to know when m is 30 milligrams, what will t be? Okay, now I don't like rewriting the equation when I can do it all in my calculator. So what I'm going to do is just divide the 30 by the 100. So Yeah, 30 divided by 100 is 0.3. So I just go 0.3, enter. And there's, now, this is 2 to the negative t over 1590. You know what, I probably better show you guys, because we're going to take the natural log of both sides, because we can't take log base 2 of both sides. So I go, let's get rid of this. Okay, so 2 to the negative t over 1590 equals 0.3. So then we go natural log of both sides. So natural log of 2 to the negative t over 1590 equals natural log of 0.3. And now I bring the negative t over 1590 down . Okay, now all I have to do is divide out the natural log 2 and multiply by 1590. Multiply by negative 1590, let's say. So we've got t equals negative natural log of 0.3 times 1590 divided by natural log 2. So basically we knew the base was 2, so we had to divide by natural log 2. That's like the change of base formula you might remember from your illustrious days in Algebra 2. So we've got 0.3, change signs, take the natural log. No, wrong, cut, take 2. 0.3, take the natural log, change signs. Then multiply by 1590 and divide by natural log 2. And we end up with 2,761.77 years. Now, since this is science rather than just pure math, you can have an intuitive sense of if you got the right answer. So notice, if this stuff decayed to 64.67 milligrams in 1,000 years, then it's reasonable that it decayed all the way down to 30 milligrams in 2,762 years. So, yeah, the book agrees with us. That's always handy too. Okay, so cruising onward, we got 2 down, 1 to go. Okay, this third example is one of my favorites. We're in first example we did biology with population. This example is chemistry. Now we're going to get to a much more practical thing to think about. I'm going to take a can of Coke, and it's at 72 degrees. Because I just got it home from the grocery store, and it's not really ready to drink yet. Now, I want to put it in the refrigerator. Oh. All right, so I'm putting it in the refrigerator, and the temperature in the refrigerator is 44 degrees Fahrenheit. Okay, so we're going to be given the other condition that at 30 minutes, the temperature will be down to 61 degrees. Not quite ready to drink yet, but it's at least cooler. Now, what I want to know is, what's the temperature at 60 degrees, in 60 minutes? What's the temperature in a full hour? And then I might want to know how long it's going to take to get down to a particular temperature. So basically, we're trying to get our equation that governs this temperature. So we've got Newton's law of cooling that says the change in temperature per unit time is going to be proportional to the change in temperature. Now, it's really important. Temperature is capital T, time is small t. Temperature is capital T, time is small t. So delta T is going to equal the difference in temperature between the 72 degrees and the refrigerator temperature of 44 degrees. So, actually, let's just keep this. T minus 44. Okay, so now what we're going to do is we're going to let y equal delta T. So y equals T minus 44. Or we'll say T sub O minus 44. Okay, so y is T sub O minus 44. And so that means y sub O equals T sub O minus 44. And so that means y sub O equals 72 minus 44. So what we just found out is the initial temperature difference is 28 degrees. So our initial temperature difference from 72 to 44 is 28 degrees. So that's our y sub O, which is the original delta T. So now what I have is dy dt equals ky. So dy dt equals ky, what can I say? That y equals y sub O e to the kt. Remember, whenever I get to this, I can always go y equals y sub O e to the kt. Okay, so now I'm ready to plug in initial conditions. So I know that at 30 minutes, it's down to 61 degrees. So I'm going to plug that in. So at 30 minutes, the temperature is 61 degrees. Let's do one more thing first. So y of 30 minutes is going to be the temperature difference at that time. So what is that difference? It's going to be 61 minus 44. So y of 30 is going to be 17 degrees. So basically 30 minutes into my cooling, my temperature difference is now down to 17 degrees. So now I can put this into this equation. So 17 is my temperature difference at 30 minutes equals y sub o. Well, what's my y sub o? 28. E to the kt. And what did we say time was? 30 minutes. Okay, so notice we have an equation again where all we have to do is solve for k. So this should be you should be seeing this pattern, how we work this. So we're going to solve for k by dividing by 28, taking the natural log of both sides, and then dividing out the 30. So k ends up equaling approximately negative 0.01663. Okay, so now I have the equation y equals y sub o, which is the original temperature difference. Wait, just say I'm recording. I should be done in just a few minutes.
Oh, wait, I'll come back because I have to clean up the field a little bit.
Okay.
All right.
So y equals y sub o e to the k t. Now, what we could do is, this is temperature difference. If I want an equation with just temperature, then I can say, I'm going to go back to y equals t minus 44. And so if y equals t minus 44, then that means t equals y plus 44. Okay, so that means I can go t equals 44 plus 28 e to the, you thought I forgot that negative, I knew it was there all along, to the negative 0.01663 t. Now here is a more usable equation. So at this point then, anytime I can tell you what the temperature is, and any temperature I want, I can tell you what the time is. So let's try an example. If we want to know what the temperature is at at 60 minutes. So if half an hour got me down to 61 degrees, how cold will the Coke be at 60 minutes? So the temperature at 60 minutes is going to equal 44 plus 28 e to the negative 0.01663 times 60. Okay, so crank that puppy on out, and that temperature is going to be 54.3 degrees Fahrenheit. Now that's not bad, but what if I say I need my beverage to be 48 degrees? It's got to be down to 48 degrees because I don't drink Coke any warmer than 48 degrees. So, okay, let's check that out. So if I want 48 degrees, then I just go 48 equals 44 plus 28 e to the negative 0.01663 t, and I'm solving for t. So I'm going to subtract out the 44, So 28e to the negative 0.01663t is going to equal 4. So e to the negative 0.01663t equals 4 over 28. So I take the natural log of both sides, and negative 0.01663t equals natural log of 4/28. And then divide out the 0.01663, so t equals natural log of 4/28. Now notice that's less than 1, so that natural log is going to be negative. So when I divide a negative by a negative, I'll get a positive. Okay, so let's check that out. So I'm going to go 4, enter, 28, divide, take the natural log of that puppy, and then divide by 0.01663. Change signs, divide, 117.012. So I'll settle for 117 minutes. So 117 minutes, or 1 hour and 57 minutes. This beverage will be down to a frosty 44 degrees. I'm sorry, 48 degrees. So that's it. So the key thing here is we're starting with y equals y sub o e to the kt. P equals p sub o e to the kt. M equals m sub o e to the kt. T equals t sub o e to the kt. And what we're doing is we're getting it into an equation where you've got t equals something times e to some number times t, and then any temperature I want, I can find out what the time is. Any time I want, I can find out what the temperature is. So that's it. Have fun with these.